Hello everybody, my name is Thias Guns and I am a professor in AI at the KU Leuven and VUB in Belgium, Europe, and I'd like to welcome you to this tutorial on CPMpy, a Numpy-based CP modeling environment. Now, before we get started, just to make sure that we're all on the same page, so what is constraint programming? Constraint programming is a family of techniques for solving constraint optimization problems. And examples include vehicle routing, where you can have lots of side constraints, also scheduling and machine to tasks, to jobs, jobs to machines with lots of side constraints. Configuration problems, again, a lot of dependencies and requirements on the different components. But CP is also used to solve a wide variety of graph problems and mathematical puzzles. Now, one of the key ideas in constraint programming is that of modeling, where a model is a collection of variables, and each variable has a list of the available values that it can take. And so typically this is finite domain integer, and the domain represents which integer values that it can take. And then a set of constraints over these decision variables, and optionally an objective function. And given such a specification, you can then use one of the many existing and highly efficient solvers to find a solution, so an assignment to the variables for this problem. So let's look at an example. Let's look at the knapsack problem. In this case, you're given a knapsack, a backpack, which has a certain capacity, which for this example is 15 kilograms. And you're also given a list of items, and each of these items both have a weight in kilograms and a value. And so the goal of the knapsack problem is to get to fill your backpack in such a way that you maximize the total value without exceeding the capacity of the knapsack, of the backpack. And so let's look at what this means in terms of variables, constraints, and objective. So the variables, in this case, we're going to have a 0, 1 variable for each of the different objects, so the green object, the blue object, and so forth. And then the constraint, well, there's only one constraint in this case, namely that the sum of the weights, as the green one has weight 12, the blue one has 2 kilograms, so that the sum of these weights, depending on whether they take the object or not, that the total sum of those that we do take is below or equal 15 kilograms. And the objective is somewhat similarly, so the objective is to maximize the sum of the value of those items that we take. And so it's 4 if we take the green one, 2 if we take the blue one, and so forth. And then this can be solved and you will find a solution. All right, and so CPMpy is all about specifying and solving these kinds of problems. We have a nice documentation, which is a good starting point, getting started guides, documentation, API, and so forth. And of course, this tutorial will show a number of these elements step by step. So let's have a look at the knapsack problem in CPMpy. And so here, we define and we instantiate the model. We create a list of 5 Boolean variables corresponding to these. So decision variables corresponding to these. And then we specify the constraint pretty much the way that we write it in pure mathematics. And we also say that we want to maximize this objective function, similar as to before. And then we can call model.solve, and it will call a solver. And if you then print the values that each of these decision variables have, you will see that in this case, the optimal knapsack contains all the objects except the first one, so except the green one, all the other objects fit in the knapsack. All right, and maximize the value. So why CPMpy? Why did we create a new kind of a modeling language in Python? Well, the CP community itself, of course, has a rich tradition in constraint modeling languages, including Minizinc and Essence Prime, for example. And in many cases, it refers back to this paper, this position paper that Eugene Freuder wrote almost 25 years ago, which says that the holy grail in computer science is basically that the user can specify the problem and then a solver solves it. And so if I can be a bit controversial, then I would say that I think that we reached it. Okay, so these existing modeling languages, Minizinc and Essence Prime, I think they're actually fantastic, and I think that They really allow you to express your problem, you specify the problem, and then you use one of the available solvers to solve it. So if we reached it, does it mean that the work is over? And the answer is, of course, not. And that is, there's a large trend in existing AI subfields where we go beyond NP, so where we go beyond solving one individual constraint programming, but where we actually want to solve a problem with an algorithmic approach that requires solving a sub-problem with a CP solver many, many times. And so where we don't use, where not the entire problem is specifiable as a finite domain constraint optimization problem, but where we do have sub-problems for which we want to use a CP solver as an oracle, and so we can query it and ask for the answer. So this really is a trend in AI today. And in many cases, people use SAT solvers or SAT modular theories or mixed integer programming solvers as sub-problem solvers. But we believe that there's actually a growing need to be able to use more high-level solvers like CP over finite domain integers in this kind of setup. So that's one part of the motivation. But there's also a more practical motivation, and a more practical motivation is that you might have your problem specification, like this specification of the Knapsack problem, and it could be in any of the existing languages. And then you want to actually solve some of these problems. So you have your CP model declaratively written down, but where does the data come from? And in our case, we do a lot of data science. So the data typically comes from Python code that we have that does some data analysis. Now, if you have a solution, you might want to graphically visualize it. And for that, at least in our case, again, we would use some of the excellent Python libraries to visualize that, or even just to plot with matplotlib to plot some of the results and the runtime comparisons and so forth. You might also want to compare different formulations in papers. And again, typically this would be with Python code where you run the different versions and then you compare the values and so forth. You might also want to check what solver parameters, again, some imperative code, which is typically in Python. And in our case, we also work a lot with the combination of machine learning and constraint solving. And in this case, we have the machine learning, which is in Python, which uses these scientific libraries in Python. And now we need to feed it into the solver. And so from the practical side, actually, if most of what we do is in Python anyway, why not use Python to model the problem as well? And starting from that point of view, this is how CPMpy was created. And so what CPMpy really is, I think there's three key defining properties. The first one is that it is about modeling CP problems, and it is in Python, so embedded in Python. The second one is that it is based on Numpy, and Numpy is the basis of almost all scientific libraries in Python, and it allows you to very efficiently work with arrays and use those. And so CPMpy itself, to be compatible with all of these other scientific Python libraries, also uses Numpy arrays as basic data structure. And then thirdly, is to have direct solver access. So because you're in a programming language, why not expose the solver access more directly? So these really are three key properties that set CPMpy apart from other modeling languages. Now, the first example of being in Python is that the installation process can be very smooth. So CPMpy is part of pip at the packaging index, and so installing it is just a matter of running pip3 install CPMpy, and this will install CPMpy. But CPMpy doesn't contain any solvers. The default solver is ORtools, and that one also exists in pip as a package, so it's a dependency. So when you install CPMpy, it will automatically also install ORtools and its CPSAT, highly efficient award-winning CPSAT solver. And so just one line and you're ready to go. Then you can open some Python script and you can write from CPMpy import star, create some variables, make a model, and solve it. Okay. All right. So I said, so the first one is Python, and second one is that it's Numpy-based. So what does it mean that it is Numpy-based? There's three properties and also advantages, as we will see. So the first one is that all variables are Numpy tensors. So what do I mean with that? As we create an individual variable, so here you see v is a Boolean variable, then it's just an individual variable. But rarely do you need individual variables when you model CP problems. In most cases, you will need arrays or matrices and so forth. And so creating an array is nothing special about it, because this variable constructor automatically creates Numpy arrays when you tell it to. And how to do that is that we use this property that's common in Numpy, namely the shape, which specifies the shape of the n-dimensional tensor that you want. In this case, we just want a list with 5 elements. So if we say shape is 5, then this will create a Numpy array with 5 Boolean decision variables in it. You can do the same for integer variables. Then it's called infar, the factory method. And so you call infar. You have to give it a lower bound and an upper bound on what the integer variables can take, as well as a shape. And so if you say 5, it means it will give you a list of a Numpy array, actually, of 5 decision variables with a value with a lower bound of 1 and upper bound of 9. Now, it doesn't need to be a simple list. If you give the shape, if you give it 2 values, then this will be the shape, the size of the first dimension and this of the second dimension. So if you say infar between 1 and 9 with a shape of 3, 3, it will create a 3 by 3 matrix. All right. Now, it doesn't need to be limited to a matrix. Actually, this shape can be any n-dimensional specification, and so the number of dimensions as well as the size of each of the dimensions. So, for example, if you say 2, 3, 4, then it creates a 3-dimensional tensor with two in the first dimension, 3 on the second dimension, and 4 on the last dimension. All right, and I think a beautiful example of this is in this code, which is for the end puzzle. We will see it again later, but so it's like a sliding puzzle, and you're giving a starting configuration, which is a 3 by 3 matrix, and we're going to decompose it into different steps, where in each step you can take a certain action. And so what we actually do is we create this three-dimensional array, where k is the number of steps, and then it's a 3 by 3 for the other dimensions. So you repeat this k times, and this just works. All right, so we know how to create decision variables. A second nice property of using Python is to do operator overloading. So if you wanna add 2 variables to each other in Python, you just write x plus y. If x would be 3, for example, and y would be 5. But we can also create these variables and put this CPMpy decision variables in it. And so we here create 3 decision variables, integer decision variables between 1 and 9 into these variables. And if you write x plus pi, because of operator overloading on the decision variables, this actually automatically creates the expression, this decision variable plus that decision variable. Right? And the same for the multiplication operator, but also other operators like absolute value. And so basically, you can use your standard Python operators the way that you would use them on constants, but you use them on CPMpy decision variables, and this automatically creates expressions, so which can then be used as constraints. For example, we can create an array of 5 elements and just write sum of A, and this will correctly translate into a symbolic representation of sum of A, so sum of each of these elements. So here's a more complex example. So you just write some arbitrary expression using Python's built-in operators, and this automatically gets translated into a valid expression over decision variables. So let's have a closer look at it. And so what happens actually when you write this? So if you look at C itself, then we see that C is an expression of the type comparison, and namely an expression of type comparisons of the equals. All right, and so the right-hand side of that is this decision variable, and the left-hand side, so x null, that's another expression, namely an operator, namely the absolute value operator. Right, so although you write standard Python on top of the decision variables, it automatically creates a CPMpy expression tree. All right, now this is where it becomes more convenient also. And so you can do your array indexing can be Python style indexing. So if we create, for example, a 4x4 matrix in this case, and you can use the notation, which is common in Python, that you say, okay, I want for the first dimension, I want the element at index 0, and for the second dimension, I write colon, so I want all of them. And this effectively gives you the row at index 0. And you can do the same for the column. So you want all of them for the first index, but the second index has to be set to 0, and this actually gives you the column. And you can also do a more detailed range iterator, so all of the rows and only columns 1 up to and without the final one. So 1 and 2, only columns 1 and 2. So this works. If you write a lot of Python, this will be natural to you. But we don't have to limit ourselves to Python style indexing. We can also do Numpy style indexing. And what does it mean? In Numpy, you can define an array, a Boolean array, so containing true and false, of the same dimension of another array. So here X is our array of decision variables. And if we create another array with Boolean values of the same dimension, then we can use that as a selector on that array. And this will basically say, give me all elements of X that have true at the corresponding index. And so this, in this case, to be the 0th and 1, 2. And so the 0th and the 2th element, and indeed it returns this. Now these indexes, they don't have to be Boolean arrays. They can also be expressions that evaluate to Boolean arrays. So for example, ranging from 0 to 4, and then checking whether these numbers are even, and if so, it will return true, and if not, it will return false. And so 0 to 4 without 4, and so the answer is again 0 and 2. And that's one thing that will be convenient, but another nice thing is that in Numpy, there is this central concept of vectorized operations. And vectorized operations means that you don't have to write out all of your loops. You can just do operations on vectors if they have compatible shapes, if they have the same shape. For example, if we have two arrays of integer decision variables and they have the same shape, namely 3, and we want to do a pairwise addition of each of the elements, then we can just write x plus y, and this will automatically see, they have the same shape, so we create a new array, again of the same shape, with the pairwise additions in it. Okay, so this vectorized operation is automatically translated into the pairwise decomposition. And the same for other operators like an equality check. And so x has a shape of 3. This array also has a shape of 3. So automatically it is translated into x0 has to be equal to 1, x1 has to be equal to 2, and x2 has to be equal to 3. All right. Now, a final nice thing that I want to highlight is that Numpy also has this concept of broadcasting. And broadcasting means that, in this case, this is still an array of size 3, but this is not an array. It's actually one individual element. And so what Numpy will do is it will broadcast that individual element to the right shape. So it will copy the 1, in this case, 3 times, so that you have x on the left side and an array of size 3 with always the same element, namely 1 on the right side, and then it will do that comparison. And so here you can see the broadcasting on 1 means that this will result into an array where we have the pairwise comparison x0 equals 1, that's the first element, x1 equals 1 is the second element, and x2 equals 1 is the third element. Okay, so let's now see this in action. So every variable is a Numpy tensor, and we have operator overloading and array indexing. Now, a lot of what I'm going to show you is going to be natural if you work a lot in Python already. And if you haven't worked a lot in Python already, it might get a bit of used to, but believe me, you get quickly used to it. Okay, so we'll start with the Sudoku problem. This is an example Sudoku. So here we use a variable e, which is a value of 0 if a certain cell element is not given, and we just use a concrete value above 0, namely 2, 5. And so these are the givens, all the values that you see here. All the ones are not given and need to be completed by the CP program. And so we create a decision variable, so we create our matrix, in this case, values between 1 and 9, and the shape has to be the same shape as this given matrix. And we call it puzzle. Yeah. Okay, so classically, the classic way of writing down Sudoku in a CP modeling language is as such, and you define n, and then you range for I to n, and then you add a constraint for each of the rows. And so you do this for row I, so initially row 0, and then you iterate over all of the possible values for the other dimension, so row j in range n. So this will be the first row, the second row, the third row, and depending on I and so forth. And the same for the columns. So this time you fix the column index and you range over the different row initials. Okay, so this is the way to write down all different on the rows and the columns. Then you need to define the all different on the blocks. So let's say that you jump at the starting point of the block, so 0, 3, 6, 0, 3, 6, and then you post the all different on the ranges 0, 1, 2, for example, for the rows, and 4, 5, 6 for the columns. Let's see. Okay, so you do this for all of the blocks. You post an all different constraint on each of these groups of variables, and that's the basic constraints. Now you still need to restrict the puzzle values itself, so for each of the rows and the columns. If in the given puzzle it's not equal to e, so if it has an actual value, then you restrict the decision variable on that index to be equal to the given integer. All right. Now in CPMpy, with its Numpy arrays and advanced indexing, this is how you can also write it. And so the key idea is that you don't have to write many of these iterators by hand. So to have the constraints on the rows, we can make use of the fact that we can iterate over all elements of the first dimension just like this. So for row in puzzle, that gives us all elements of the individual. And then we just post the all different on the row directly. And for column, we can do it similarly, only in this case we use the Numpy built-in transpose. This will transpose the matrix in such a way that all of the elements of the first dimension are, in this case, the columns. And then we write this, okay? So for the blocks, here we use instead of writing out the ranges, we can just abbreviate this and put this in the matrix operator directly, e to I to I plus 3, j to j plus 3, and this will actually unfold to exactly the same thing automatically. And then my favorite is how to post the actual given values. So here we use a combination of two things. We first use a selector. So instead of looping over all of the elements and checking whether given is of that element is different from E, we can just write this as a selector like this. So given not equals E will give us an array, actually a matrix of the same shape that says true, false, false, true, false, and it's only true where given the given element is different from E. So that's a selector. We apply this selector both on puzzle and on given, which means that the two will be tensors of the same dimension. And then we say that the ones that remain, so the ones that are true, for them, they have to be equal to each other, these individual variables. So this works nicely. You don't have to write out the loops. Okay. Now let's look at a second, more realistic example. So this is or at least more industrial type example. So this is the job shop scheduling problem. You're given a number of jobs. They each consist of tasks that have to be run on a specific machine and that have a certain duration on that machine. So job 0, its first task has a duration of 3 on machine 0, 2 on machine 1, and 2 on machine 2. Okay, and that's for each of the jobs. So as decision variables, we will use one matrix of decision variables for the start time of each task on each machine, and also the end time of each task on each machine. All right, so the classic way to write out this in a CP model is that you want to enforce that the end time is equal to the start time plus the given duration. So you iterate over all jobs and all machines, and then you say that end time of that element equals start time of that element plus jobs data as the duration. Now notice that these two are switched, their indices, which is just the way that we got the data. All right, and then precedence constraints. So in this case, a machine first has to finish its tasks. Sorry, a job first has to finish a task on machine 0 before it can run a task on machine 1, before it can run a task on machine 2. And so that's what this expresses. So the end time at the first machine, at the smaller machine, has to be smaller than the start time at the later machine. And then we can only run one task at a machine at the same time, and that's this disjunctive constraint that you write like this. And then the make span, we can use a global maximum constraint to specify that the make span is a maximum of all of the possible end times. Now in CPMpy, this is how you'd write it. So first of all, you don't have to write out the loops to impose these end times because the dimensions match. So you can just write end times equals start times, and then I told you that jobs, the data was actually transposed. So we first transpose the jobs data so that it matches those of end time and start time, and then we can just write this expression and it will automatically be unfolded to exactly this. And so to an array of each of the individual elements. Also for the precedence constraints, we don't have to write out the initial loop. We can use the colon notation. And also for the no overlap constraints, we can use the colon notation, and it will vectorize it, and it will work just fine. And then finally, for the make span, instead of writing out this global constraint in full, if you know that it exists, you can also just use the built-in Python max operator. You say max of end time, and it will create the correct expression. And you can minimize that. All right, now if you have this job shop schedule problem, then you probably want to have a look at the outcome. So for example, you would print what the make span value is, and then you want to visualize the result. For example, such that every row is a machine, and such that you see the task identifier here on machine 0. It first runs task 1 for 2 time steps, then task 0 for 3 time steps, and then it doesn't use the machine anymore. So we added some -8 value. And so you can use some Numpy style programming to make such a matrix and print it. Fine. Now, you might actually also want to visualize the result because this ASCII art takes a bit used to reading. So why not visualize the result? And actually for job shop, Alexander Schiendorfer has done a very nice job of creating visualizations for typical CP problems, including the job shop scheduling problem. So he uses the PIL library, Python library for image manipulation. And so we can take that code, change just a tiny little bit of it, and voila, we can get a graphical representation of our solution. So it's again the same thing, job 1 for 2 time steps, job 0 for 3 time steps, and not used after that. And of course, this is much nicer to see, and it's just a matter of replacing the ASCII code by some code that generates that visualization. All right. Now, another problem that I want to show that shows some of the properties is the end puzzle problem. It's a problem that's a bit tricky to model in CP, or at least I hadn't considered it before. And that's because it's actually a problem that falls in the planning as set approach. So it's a planning problem, meaning that you have to plan for a number of steps ahead, what kind of actions you're going to take at each step in such a way that that you can find a solution, so a plan at each actions at each step that lead to the end solution. So there's an approach called planning as set that showed that you can use set solvers or CP solvers more generally for that. So the start, and we're given some kind of start. So this is a sliding puzzle. I don't know where I put it, but it's like a typical children's game where you need to reconstruct the image by putting the tiles in the right order, and you have one blank space. The blank space is a 0, so you can move the 4 down, for example, and so forth. All right, and so that's the desired end goal. And so we're going to define a model for this problem up to a maximum number of steps. So there's a maximum number of steps, k, and then we create this k times 3 matrix that represents each of the possible action steps that we modeled. All right, and this is what it looks like in CPMpy. So first of all, we're going to say that the first state of this three-dimensional matrix has to be the start state. So the first dimension is the step. So if we take x0, then we automatically get the 3x3 matrix of x0. And so we can equate that, and so we can say that the 3x3 of the first step, so index 0 of the first dimension, has to be equal to the puzzle start. And we can say the same for the end state, namely the very last at the first index, the 3x3 at the very last of that k times n matrix has to be equal to puzzle end. All right. Then we need to define the allowed moves. So when can you slide a puzzle? Only if there's so a puzzle piece can be slided up, left, right, or down, but only if it doesn't cross the border. So you cannot have position -1. So we have all of the possible moves, and then we compute for a given position whether this is between 0 and the dimension. Okay, and this returns a list of all of the possible moves that you can slide one certain position at a certain piece to. Okay, so this is just some generative code. This generates these lists. How do we use it now? Well, we're going to model the transition for every step in our planning problem, and at every step we have a first invariant that says that all of the values have to be different. So we put in all different on the elements of that step. The other invariant is that only the 0 position can move. So between two subsequent steps, they actually all values have to be the same unless, or it was a 0 in the previous step, or the 0 is at that location at the next step. All right, so these are the three possible cases. Either it was a 0 in previous or next, or it has to be exactly the same value from one transition to another, from one state to another state, subsequent state. And then for each of the positions, we have to determine the reachability. So the 0 position, the blank position, can only be at that specific location if it was at a reachable state in the position before. And that's it. So if you do this, then you give it the k up front, and it will generate a model, and you can use Solver to solve it. For example, if we use that puzzle that I showed before, and we tell it, okay, find a solution in 10 steps, solve it, and it will tell you, it's not satisfiable. You cannot reach the end state in 10 steps. So we can increase the step size to 100, and then it will say, yes, actually in 100 steps, you can find the solution. It actually took 2.2 seconds, and then we found an optimal planning. All right. Now, knowing what number of steps you need is typically not an easy task. And if you do it manually, you might try 10, and then 100, and then maybe 200, or maybe try 12 first, 15, and so forth. So, but we can also do this programmatically, right? Because this is a programming language. So we can say, well, let's start at a small step size, something like 5, and let's always try to increment it with 4 in case it is not satisfiable. And that's exactly what this piece of code does. So we initiate the end puzzle for a certain k, in this case 5. If it cannot be solved, then fine. We increase the maximum number of steps. We rebuild a new model. And so we build a new model with up to this new maximum number of steps, and then we solve it. Okay, and if we do this, then we can see that it's fairly quick to determine that there is no solution that can be found. And then at 21, it says, yes, now I can find a solution, and you're done. Okay. So because we're in this programming language, this is actually quite easy to do, write down and automate. Now, you might still not be very satisfied by the efficiency of the solver, and then you might wonder, well, isn't there some parameter configuration of the solver that actually solves these problems quicker? Because we're going to do it over and over and over and over and over. So why not take a small problem, try out a few number of parameter combinations, and see which one is best. And this is something that can also be automated. So we actually have an example in CPMpy that does this hyperparameter optimization for the OR tool solver. And so if, for example, we consider these 3 hyperparameters of OR tools, we try all possible, so for example, for linearization level, it will try either 0 or 1. For symmetry level, 0 or 1 or 2. And then we can write this little piece of code that generates all combinations, runs the solver, and stores how fast it was. And so if we run this, of course you need a bit of patience because it will run all of these combinations, but then it will say, actually the fastest to solve it was in 0.078 seconds, and it was this configuration. No probing, level 1 linearization, and no symmetry. Okay, and once you found this, you can actually initialize the CPM OR tool solver and tell it to use those parameter configurations. And what do we see? And so we trained it. We were looking for the hyperparameters just for a step size of 20, which is relatively small and fast. And now we use the same configuration for 100. So if we don't use our tuned parameters, it took 2.2 seconds. And if we now do use our best parameters, then it only takes 0.4 seconds. All right, so with exactly the same step size. And so this is one of the things that you gain by being embedded in Python. All right, so that's the end of part 1. And so the main point in this part 1 is that CPMpy is a CP modeling library in Python. It's aimed to be compatible with existing scientific toolkits. So it's based on Numpy as a basic data structure, and it gives you direct solver access, which allows you to do, for example, the hyperparameter optimization of the previous slide. All right, so that was the end of part 1. Now, for part 2, we will look at this property, this key motivation that I told you, to use CP as an oracle. That means to use CP to do repeated solving. Okay. And part of this motivation is because in our lab here at KU Leuven, we work a lot in problem settings where we need to use CP as an oracle. And actually, I was awarded this very nice ERC Consolidator grant. And the research plan for that grant and the things that we want to do in the future is to work towards conversational human-aware technology for optimization. Now, what does this mean? Well, we want to work towards a setting in which you can do a co-creation between the user and the solver of constraint optimization solutions. And so I believe that there's 2 key parts that are needed to achieve this. And that is that we need to make the solver smarter, in that the solvers need to be able to learn from the user, for example, user preferences, but also from the environment and what the typical situations in the environment are. So this requires a lot of machine learning, integration between machine learning and solving, for which you need to do repeated solving. And the other aspect is that we want to work towards making solvers more conversational, and that means being able to ask for explanations from the solver and to have stateful interactions with that solver. And this, of course, also requires repeated solving. And so actually, I'm still looking for postdocs to join me in this project. So if you find this stuff interesting, do reach out by email, because also in the coming years, I will have positions available. But so within this large 5-year project, we have a big need for this repeated solving. And I'll give some examples based on our current research where we use CP as an oracle. First of all, with a focus on explanation methods, so methods for explaining constraint programming solutions and non-solutions, and then in the second part on integrating machine learning with constraint solving. And so both require this repeated solving. Okay, so let's start with explanation methods. And the simplest type of interaction with the solver that you can imagine is that where you want multiple solutions. And so I actually worked with the Minizinc authors a number of years ago, as well as Andrea Rendel, on a mini search. And mini search was a domain-specific extension to Minizinc that allowed you to express these kinds of meta search problems, so where you need to solve a problem repeatedly and add some constraints to the model. Now, as we wrote in that paper, you can do the same for embedded modeling languages like CPMpy. And so I, of course, took care to make sure CPMpy was constructed in that way. And because Python itself does all of the program execution, it's mostly a matter of defining the right kind of API on how you interact with the model or the solver object. So here's an example of enumerating all possible solutions using blocking clauses. So you create your variables, you create your constraint, you add it to a model, and then you can write while model.solve. And that's because when you call model.solve, it doesn't give you a status object. In most existing CP solvers, you get a status object when you call solve. But for CPMpy, what it does is it returns true if it found a solution, and it returns false if it did not find a solution. And so you can use that to immediately process in your code. So while it found a solution, you will print the value of the decision variables, and then you will add an additional constraint. You will add a new constraint to the model that says the next solution cannot be such that all of the decision variables get the same value as that you just found. All right, so you write this, and we've seen before that you can use the plus equals operator to add constraints to a model. Well, you can do this even if you've already solved the model before. You can just do that, call solve again, and then it will solve this new model that includes the newly added constraints. All right, so in the mini search paper, we also had an example with diverse solutions, and this is what it would look like in what it looks like in CPMpy. And so we first define a diversity measure, for example, the Hamming distance. And Hamming distance is the number of variables that have a different value. And so in this case, we can say, okay, we can write this in a vectorized way. So when x is different from y, so this checks which ones are different, and you sum over that. Okay. So what do we do now? We still have our model. We will store each of the solutions as we will find them, because every time that we find a solution, we want to, in the next iteration, we want to find the solution that is most diverse with respect to all of the previously found ones. So we have this store while model.solve, and we print how many element in the store it is and what the assignment is. Then we add a blocking constraint as before. We add the element to the store, and now we change the objective function and we say, okay, the next solution that we want to find has to maximize the Hamming distance between the current solution and all of the previous solutions. And so the Hamming distance between the solutions you're currently generating and all of the previous ones. And so the way that this is, the reason that this works is that you can actually change the objective function even if you've already solved it before. And if you now call solve, it will use this objective function and not the previous objective function, obviously. All right, so you override the objective function basically. Okay, and that's it. Now you might be wondering, isn't that actually bad for performance that you're resolving from scratch each time? And to give you just a bit of an insight of the mechanism behind, and to show you that the answer is no, and that this actually supports incrementality, I need to explain you the difference between two execution mechanisms within CPMpy. Namely, we have a lazy execution mechanism, and we have an eager execution mechanism. So if you create a model, so the model object follows a lazy execution mechanism. That means that the model simply stores CPMpy expressions. It doesn't do any kind of operations on it. It just stores the expression. So you can overwrite it, you can change it, whatever. It just stores them. And only when you call solve will it translate it to the solver API and so forth. And so there is a little bit of overhead with respect to CPMpy that it builds the entire model to the solver and calls it. And so if you do this for this example, this time we've increased the shape to 30. It takes 1.4 seconds. Now, that's the lazy execution mechanism. Now, the solver interfaces themselves. And so this is the CPMpy interface to the ER tool solver. That one implements an eager execution mechanism. And that means that it doesn't store the expressions. It doesn't store the CPMpy expressions that you add to it. It immediately translates it to the solver and calls the corresponding solver API constraint addition routines. And so it immediately, if you add a constraint to it, like here, it immediately posts these constraints to the solver. It doesn't keep the state itself, it's the solver that keeps the state. And so what does that mean? When you call this, CPMpy will translate the model that is given and send it to the solver. And at that point, if you call solve, the solver will give you the answer. And if you add a constraint, only that individual constraint is sent to the solver, which needs to support doing this. And then when you call solve again, it's immediately again the solver that gives you an answer. And so the overhead of CPMpy, the thing that CPMpy does is really minimal, and it's only here at the individual constraint level. And you can see that here the runtime was 1.4, and here the runtime was 0.6. So if the solver supports incrementality, which our tools doesn't, then it would be even lower. All right. So let's look at a number of things we can now do. And the first one, with exactly the same API, is that of finding minimal unsatisfiable subsets. Now, a minimal unsatisfiable subset, let's here take this list of constraints. The first three constraints, they have this circular bigger than. And so it says that x0 is bigger than x1, x1 is bigger than x2, and x2 is bigger than x0. Okay, this is not possible. This will be unsatisfiable. Now, and of course, here we know what the unsatisfiable subset is, but imagine that this is part of a bigger model. So you have other types of constraints, including arbitrary complex expressions. Okay, so in CPMpy, it doesn't care whether the constraint that you write is one individual elementary constraint or whether this is actually a nested expression. For CPMpy, that doesn't matter. So you have your list of constraints, and we now want to find the minimal unsatisfiable subset of constraints that makes this model or this set of constraints unsatisfiable. And so what we will do is, this is a deletion-based approach that's implemented here. So we'll delete each of the constraints one by one. And so we iterate over all of the positions, and then we take all of the constraints from 0 up to I, and all of the constraints from I plus 1 up to the end. And so everything except constraint I. And then we check if we leave out this constraint, is the model still unsatisfiable? And so actually, if you call solve and it's satisfiable, then that means that when you remove I, it is no longer unsatisfiable. So I is one of the elements that makes it unsatisfiable. So we need to keep I in the constraint set. And so this I's element is one of the unsatisfiable constraints that makes it one of the constraints. Okay, so we keep it in. If, however, our model is still unset, even if we delete that one constraint, then it means that we don't need that constraint, right? We delete it, it's still unset, so it's not part of the minimal unsatisfiable subset. Okay, so we delete it, and we continue with the ones that are remaining. And so if you apply this on this little set of constraints, and for the first one, it tells you yes, so it needs to be in a mus, and the other one says no, you can remove them, everything is fine. Okay, so that's a simple deletion-based mus algorithm. Now, if you know about the set literature in set, they have a much more efficient way to do this, and that is because they can work with assumption variables and they can extract an unsatisfiable core over these assumption variables. So what does this mean? So well, let me first tell you that nowadays, so CP solvers, there's a family of CP solvers, namely CP solvers based on set technology, lazy class generation. They can also give you an unsatisfiable core. So we can use the same mechanism also for CP solvers today, and that's what CPMpy supports. But let me first explain the mechanism. So instead of trying different kind of subsets and reposting and creating new model with that subset of constraints, the idea is to first create indicator variables and add a constraint that says that this indicator variable implies a constraint. Okay, so we create a Boolean variable here that implies this constraint, a Boolean variable here that implies this, and also a Boolean variable here that implies this constraint. Okay, so for CP solvers, it doesn't matter that this is a nested expression. CPMpy will handle this appropriately, and you still have just your single assumption variable. Okay, so we create these Boolean variables, these indicator variables, and then we call the solver and we say, assume that all of these indicator variables are true. Okay, this will be unset, and then we can ask the solver to extract the unsatisfiable core. So it has its own mechanisms to already reduce the set of constraints that make it unsatisfiable, and that's this unsatisfiable core. So we can get this core, it will be much smaller. So if you do this on a model with thousands of constraints, the unsatisfiable core will already be only a handful of constraints, and then we can do our deletion-based approach simply on the constraints that remain in the core to see whether we can still delete any of them. And so in this, the code is almost identical, only that we don't reconstruct the model, we just reduce the set of assumption variables. So we check, what if we don't set that assumption variable of that constraint to 1? Is it now still unset, yes or no? All right. And so this is actually code. This is the way that it is implemented in PySet. So how you can do deletion-based method extraction in set solvers. And we can just implement the same thing on top of CPMpy. And in case you're using a solver that supports assumption variables and core extraction like OR tools, then this still works. Okay. Now, that was the first algorithm. Another nice algorithm is the Markov algorithm. So why is this a nice? So this one actually does enumeration of minimum satisfiable subsets and maximum satisfiable subsets. So what's nice about this Markov algorithm, why I show it here, is that it actually uses two solvers. It uses a subproblem solver, which will be a solver that checks whether a subset of constraints is true or not. And it also uses a higher level solver, a map solver, a kind of master solver that simply generates candidate combinations of constraints. All right, so we ask for a candidate combination of constraints. We check whether that one is indeed satisfiable. And if it is, we will grow it to a maximum satisfiable subset, and we will block all of the maximum all of the subsets of that maximum satisfiable subset. And so our map solver can no longer give any of the subsets of something that you already found to be maximal. If it is unset, then we actually seed it from the unset core. We try to shrink it further using the deletion-based algorithm just shown, and then we get a mus, a minimum satisfied subset, and we block all supersets of that mus. And this we can just keep doing until we've enumerated all MSS and MUSs. So at this code, you can simply run it. For example, on the example below, it will generate the MUS, and then it will generate each of these three variants of the MSS, which always removes one constraint and adds the other two. All right, now that's for minimal and satisfiable subsets, but in our recent work, so ECI 2020, we actually worked with optimal unsatisfiable subsets. So not just minimal, but cost minimum. And the way to do this is to use an implicit hitting set algorithm. And so if you use an implicit hitting set algorithm, if you implement this, you also need two solvers. So the subproblem solver that will check whether that combination of constraints is satisfiable or not. And then in this case, the master problem solver, this is a hitting set algorithm. And for optimal unsatisfiable subsets, it's actually an optimization algorithm. So it tries to find the optimal hitting set. And so this is actually running code. This is valid CPMpy code. You and so while your loop continues, you call the hitting set solver and you ask for the most optimal candidate hitting set. You get the elements that are true of it. You check whether it's unset. If this optimal hitting set is unset, then you know that you found the cost optimal hitting set. And so then you're done. And if it is not, then you know that it's actually a satisfiable subset, meaning that the complement of it, at least one of those has to be unsatisfiable. So you need to find a new hitting set that hits at least one of those elements in the complement. So you build the complement, you add you add this to the hitting set solver, and you continue. Okay, so this is an implicit hitting set algorithm in CPMpy. Now, the way that we actually use it in that paper is to explain satisfiable problems step by step. So what does it mean to explain a satisfiable problem? And so this is, again, a small example. You have 3 constraints, and this one has a unique solution. And so the unique solution to this one is that B1 is true, B0 is false, and B2 is true. And what we actually want to do is we want to explain in small steps what combinations of constraints lead to each of these literals. And in each step, we want the explanation to be as small as possible. And small means that if you use a literal, it has cost 1. If you use a constraint, it has cost 5. And so we use these are optimal and satisfiable subsets. And for example, we can find that initially, if you use this constraint and no facts, you can derive that B is false. Then using B is false and this constraint, you can derive that B is 1. And using not B0 and B1, in this constraint, you can derive that B2. And you actually know why the solution is the way it is. So this is an example of explaining set problems that uses multiple calls that each call a hitting set solver, which each call assumption solver over and over again. All right. Now, my last and favorite example in the explanation category, this is actually work by Anton Korikov, a very nice researcher working with Chris Beck, and he will present his work at CP, so in the very near future. But we had the pleasure of meeting him before, and he gave a talk at our lab about their work, where they're looking at counterfactually explaining optimization problems. And so all of the methods before, these were for unsatisfiable problems. This is for satisfiable problems. And so this is one of the first works in CP on explaining optimization problems. And well, you should obviously read the paper and see the presentation. But the essence of the problem setting is that assume that you're given a certain optimization problem. For example, a knapsack with given values and weights. This has an optimal solution. Okay, in this case, it's this one. Now, the user might ask for an explanation and might say, actually, why didn't you find the solution that does not contain 3, 4, 6, so that doesn't have that, but that does have 2, 7. And so the user specifies this foil, specifies this partial assignment, and the user asks, how should the values corresponding to these items change such that any solution that satisfies these constraints would be optimal? So how should I change the objective function so that any completion of this partial assignment now becomes optimal? And so we'll see in a minute how the method works. But so the answer is this one. So it will be, okay, these are the values. If you use them, then this results in an optimal solution satisfying the user query, namely 2, 7, 8, 9. And to do that, you only need to change these weights by that value. And so even though 2 is here, and in the query, you didn't need to change 2, you only needed to change the other ones. So we re-implemented this in CPMpy. And the nice thing about the approach is that it uses a cutting plane algorithm. And the paper shows that you can apply this to CP as well. And here we show how to implement it on top of CPMpy. And so we have a master problem. And the master problem will propose a new set of weights, so a new value cost vector, which minimally changes the original cost value vector. And then the subproblem solver, it will check whether this is indeed the optimal solution. So that satisfies the user constraints. All right. So how does this work? So the master problem, we solve the master problem and we get this new cost factor from it. We then give it to, and we say, okay, given this cost factor, find me now the best possible knapsack, and we solve it. And then we check whether this foil-based solution, so the solution that respects the user assignment, whether it actually is the optimal one. If so, we're done. If not, we need to add a cutting plane to the master problem that says, okay, next time that you give me a cost vector, make sure that this assignment scores better than that one. All right, so we add a cutting plane and we solve the master problem again. And that's it. All right, so you can run this, and it returns, well, as part of the bigger program, it returns this. Okay, so I've now given you multiple examples on how CPMpy can be used to indeed work on making or like towards conversational, or at least explaining the mechanism behind a constraint solver. But the other key part that we need is to integrate machine learning and constraint solving. And also in that case, we will need to use CP as an oracle over and over and over again. So I'll quickly highlight 3 such settings. The first one is that of visual Sudoku. So we've seen standard Sudoku, and this was our input. This was how we model it, and then we can write some beautiful ASCII art visualization of the solution that shows that indeed CP can be used to find a solution to that. But what if our matrix here isn't given as concrete values, but as images from a picture? So for example, indeed, we're given one image for every element of the cell. It's a blank image if it's blank, or it's a handwritten digit in case the value is given. All right. So here the code that I just called over samples this from the MNIST dataset. Now in this case, we would need to classify for each of these images what the likely intended handwritten digit there is. And so we can use a convolutional neural network like a net. We actually use a pre-trained one. But the network that we use here for the example of this demo isn't very well trained. And so MNIST, you can get very high accuracies, but we here only train it for a smaller number of epochs, so it classifies some of them very well, but for others it does have some uncertainties. So it has some, is it a 9 or a 7? It's not entirely sure yet. And so this is representative for the kind of things that you would get if you would solve a much harder problem. Okay, so with that, we can actually solve. We can ask, where is it? And we can have our neural network. We can predict probabilities, and then we can ask, okay, give me the prediction. So give me the most likely prediction for each of the cells. And in that case, what would happen is that our Sudoku would not be solvable, because for this image, for example, it predicted a 2. For this image, it predicted a 4. And for this image, it predicted an 8. But that's not a valid Sudoku, so we're stuck. Now, we investigated this problem in a nice CPIR 2020 paper, and where we said that actually you don't just have to take the predictions. What you can do is you can take, instead of asking for the predictions, you can write a CP model that reasons directly over the probabilities of each of the possible clauses for each of the possible cells. And so instead of taking the predictions and solving and reasoning over that, we can actually turn it into a maximum log likelihood problem, where we take all of the probabilities and we maximize the probability for over all of the assignments to each of the individual images. And so if we would do that, we would find this kind of Sudoku. So we find a valid Sudoku. It actually corrected the argmax mistake here and here. So it took the next or third or whatever most likely assignment such that you can complete everything to a Sudoku. But it's still not a true one. This is not the true intended Sudoku, because it still misclassified this one, but it finds a Sudoku solution with this one. Now actually, we know that Sudokus have to have a unique solution, and if we would verify it for this one, we would find out that solution is not unique. So this assignment to the colored cells does not lead to one solution, but to multiple possible solutions. And so we also discuss in the paper that we can add blocking constraints. And so we first find out if the solution is unique, and if it is not unique, and while not unique, we actually block this assignment to the images, and we continue searching for another one. And so this was the previous result. And if we do this loop until we find a unique assignment to the colored images, then we do find the correctly colored image, which corrects each of the 3 prediction mistakes of before. All right. And so as you can see, there's a lot of machine learning going on the image part, but we also need to add constraints and do this iterative checking on the constraint solving side. Another example I quickly want to highlight is our work on VRP solving, where you want to learn hidden preferences from historical data. So this is a paper, this was a CP 2019 Best Student, won the Best Student Paper Award. And so obviously we can formulate a VRP problem in CPMpy, and we can use this to solve a given problem, and we compute a distance matrix based on the coordinates, and then we see that, okay, this would be the distance optimal vehicle routing solution. But in our case, we assume that there is some hidden preferences. We assume that the user, for example, there might be a city here, here, and here, and so the user has some hidden preference to group stops that are in these zones. And so we're not going to tell the solver doesn't know it, it's implicit, but based on historical instances that satisfy these preferences, we want to see whether we can learn these kind of hidden preferences and whether we can reconstruct solutions that also satisfy them. Okay, so this is the hidden preference function. We then generate data according to this preference function and compute the historic solutions based on this preference function. And then we have our own little code, and this creates the Bayesian probability matrix, which gives a probability for each of the possible arcs in the network. So instead of using distances, we will use probabilities, and then we can solve our VRP problem, and this is what it does. So this is a solution, a target solution for a specific day, so a specific subset of stops that satisfies these preferences. If you only use the distances, then you would get this kind of solution, and if you mix distances with the preferences that we learned, you would actually get this kind of solution, which coincidentally is exactly the same, but in many cases it will be much more similar to the intended solution than this one. All right, and then the last example with machine learning that I quickly want to highlight, but it's much more too complex for it can be a tutorial in its own. But so this is our work on a predict plus optimize, where we want to do machine learning of cost vectors based on the outcome after solving. So let me take it step by step. So this is for the knapsack problem. Of course, we know how to solve the knapsack problem, and we know how to solve it for different cost vectors. And this is a little wrapper class that allows you to solve it for different kind of cost vectors. And indeed, you can use it to solve a knapsack problem. Now, in this case, the values of the knapsack are not given, but need to be predicted from data. For example, we need to predict that there's energy prices or there's estimated values on some kind of bidding market. So we need, based on historic data, we need to predict the value. And that's what's going on here. So we load all of the data. All right, and then what we can do is we can first do regression on the cost vectors, so on the value vectors of the individual items. So we make a prediction for each of the items, and then we solve that problem afterwards. And what we see if we do this, is we use a standard machine learning loss for the predictions. We see that this mean square error, the standard machine learning loss function, over training, so as we increase the number of epochs, as we continue training, continues to decrease and decrease and decrease. And this is good. But if we then look at the regret, and that means the cost that we actually pay, so the difference between using the real values and the predicted values, that's the regret. So the difference, and so because we use predicted values, there might be mistakes in that, and what the cost is of those mistakes, that's quantified by regret. So we see that the regret is actually not improving. Although our loss function is improving, our regret is staying about the same. And so it means that from the optimization point of view, our machine learning model, our machine learning aren't getting any better. Now, the reason to do, or the solution to do this better is to use, for example, the SPO approach, the Smart Predict and Optimize approach. And what does it do? What does it do? Well, this is actually a PyTorch code that does the neural network learning. And so for every epoch and for every training subset, it will compute a gradient and it will backpropagate that gradient over the neural network. All right. Now, instead of using a gradient from a loss function like mean square error, we will here actually compute the gradient manually based on the output of the solver. So within this training loop, and so this is standard PyTorch machine learning code, within this training loop, we call our solver, we call CPMpy, to solve a certain optimization problem, and we compute a gradient from that. And if we do that, then we have this decision-focused learning setting. Yeah? And so actually, if we look at mean square error, it's not improving the mean square error a lot. But if we look at the regret, then we see that the predictions that it makes are improving the regret, in this case on the test set. So it is leading to better predictions from the perspective of the optimization problem. So this is really nice kind of work that really requires a very deep integration of solving, repeated solving with machine learning. With machine learning. All right. Oops. Oh, yes. Okay. So, so these were the three examples that I quickly wanted to highlight. And so, as I said, so all of this is based on using CP as an oracle, of which we plan to do much more in the future, and for which I'm still looking for postdocs, obviously. All right. So in part 2, we first of all, well, we saw that we can use CP as an oracle, and we saw how to do blocking constraints and set core extraction, use multiple solvers at the same time, implicit hitting, set algorithms, cutting planes, integration with machine learning, and so forth. Now, in the last part of this tutorial, we will have a quick look. And so this is part 3 of the CPMpy tutorial. And now we'll have a quick look behind the scenes at how it is implemented. Okay, so a first major design principle in CPMpy is that CPMpy aims to be a thin layer on top of the solver API. Okay, so it wants to be just a thin layer. And the central concept in all of the code is that of CPMpy expressions. So CPMpy is all about creating and modifying CPMpy expressions and passing it on to the solver API. So this is what the tool chain looks like. And so the user writes CPMpy code. You've seen many examples by now. As in this CPMpy code, they create a model, and a model is a list of constraints where each constraint is an expression tree, as well as one objective, which is also an expression tree. Okay, so the user creates a kind of model, and then they will call solve, meaning that they will call a solver interface. And the solver interface has, at the moment, 3 different implementations, so the Minizinc, ORtools, and PySet solver interfaces. And so what CPMpy does is it then translates these expression trees to the corresponding expressions of the solver API. So in case of Minizinc, it translates it to Minizinc text, gives it to the Minizinc Python package, which in turn will call the Minizinc interpreter, which in turn will call any of the solvers that it supports. All right, but this is where it stops for CPMpy. In case of ORtools, the default solver, and so this one you have to install yourself. This one is automatically installed. In case of ORtools actually doesn't support automatically creating auxiliary variables. So you need to create auxiliary variables yourself. In this case, CPMpy will create it. So CPM ORtools will what we call flatten the model, and I'll say a bit about what this does very soon. And then those flattened CPMpy expressions will then be translated to corresponding API calls in ORtools. Now we also support PySet. So in this case, it's only for Boolean decision variables. It will flatten the model, which corresponds to doing a side-scene encoding, and then it translates it to CNF because PySet, its interface, expects CNF as input. So CPMpy will do that for you. We'll reuse the same code here and use some custom code here, and then it will translate this to the PySet interface, which in turn has multiple set solvers that it supports. Okay. Now the code structure that we have, and so everything that has to do with the expressions is in the expressions folder. Everything has to do with transformations in the transformations folder, and everything that has to do with solver interfaces is in the solver directory. So this is what the file structure of the code looks like. And so the CPMpy Python library, of course, has an init function as is required by Python. It has the model.py file, which contains this generic model container. And then it has these 3 folders, everything related to expressions, to transformations, and to solvers. Okay, and that's it. Of course, we also have documentation, examples, and tests. Now let's have a look at what's in the expressions folder. So in the expressions folder, we have different kinds of classes that represent our expressions. And also this one, we kept quite minimal. So we have the abstract expression object, obviously. And then we also have the n-dimensional decision variable array of CPMpy, which is an implementation of the NumPy, a subclass of NumPy and the array. Okay. Then we have classes for the individual variables, namely an individual integer variable, an integer Boolean variable, and its negation. So these ones are typically hidden from the user. You don't see that they exist, but they are there, and they're all in the variables.py file. Then we have two core expressions, namely a comparison expression like equals, larger than, not equals, and so these kinds of comparisons. And we have operators like plus, and, or, minus, absolute value, and so forth. All right, and so these are implemented in core.py. And then, of course, we also have an abstract global constraint class, which is subclassed into, for example, the element constraint, the all different constraint, the maximum constraint, and so forth and so forth. Okay, now these are actually the three files that contain it. And as you can see, we don't have binary operator, n-array operator, and it's just one operator class that then has properties, and it means that our transformation rules can be quite simple. They only have to support a limited number of cases. So the transformations, there's actually much more to say about transformations than I can in this tutorial. The key concept of the transformations is that of a flat normal form. So if we look at Boolean satisfiability, then they have these nice normal forms like negated normal form or conjunctive normal form. And basically the flat normal form is a similar kind of normal form, but then for CP. And basically it's a limited nested negated normal form for CP expressions. So what this is or what this does is it's actually in line with what other languages call flattening, so the removal of sub-expressions, but we express it as a normal form, meaning that we define the kind of expressions that are valid in this flat normal form. So we have base constraints that do not have nesting, so they only involve variables and constants. Now we have comparisons constraints, and they allow one level of nesting, so they allow a comparison with some numeric expression like plus, product, divide, modulo weighted sum, and so forth. And then also reified or implied constraints, which allow up to 2 levels of nesting. And so, for example, the most kind of complex expression that this flat normal form allows is that you have a weighted sum that has to be larger than 5, and the truest value of this is equal to some kind of Boolean variable. All right, so that's the maximum amount of nesting that is possible, and this is an intermediate language. None of the solvers support this kind of expressions, but from these kind of expressions, it's very simple to map to the solver API. All right, so this is like an intermediate representation of flat normal form. All right, and then just a little bit about solvers. And so we only interface to Python APIs of solvers. And unfortunately, for CP, there is no common CP solver API. So we have to, so typically the different solvers have their own kind of Python API, and we have to interface to that. But an important key principle of CPMpy is that a solver can choose which of the expressions it supports. All right, so solvers do not need to support all of the expressions and all of the variables. For example, at the PySet, the Boolean variable, only if you use Boolean variables will it work. Otherwise, it will tell you, wait, I don't implement this. And that's fine. All right, in CPMpy, you don't have to implement everything for every solver. The solver itself chooses what it implements. So it means that we can gradually extend it, or just that in some cases, you're not going to use that solver, and that's fine. Solvers can also choose to support assumptions or not, be incremental or not, and expose their own solver parameters. All right. So that was a quick tour of the behind the scenes. And so, okay, in terms of solvers, so we currently support OR tools as a default solver, PySet and Minizinc, and we're going to add Gurobi and another MIP-like solver in the very near future. And on our wish list, for which we can highly appreciate any kind of help is to have Z3 or other CP solvers like Mistral 2 and Geese, which are also lazy clause generation solvers. All right, and then we're nearing the end of this tutorial. So in part 1, I talked about what CPMpy is, namely a CP modeling library in Python based on NumPy and with direct solver access. In part 2, I gave loads of examples of CP as an oracle and how it can be used for these kinds of repeated solving cases and problems. And then in this part 3, I gave a quick peek behind the scenes where we try to keep it light. Now, all of the examples that I showed you can be run. So we have this examples folder that contains the basic examples, the visual examples that contain the nice visualizations, and then also the advanced examples that contain what I showed in part 2. And so if you're a CP user, I warmly want to invite you to give it a try. It's a lot of fun. If you're a solver developer, then I think there's something to gain for the both of us, so we can make your solver easier to use. If you make a Python API, we'd be happy to interface to it, so please contact us. And so CPMpy is an open source project. And so we invite contributions from the community. And so you can report issues, you can add new examples and other things like clone it, fork it, whatever, on this GitHub page. Then to close off, so in terms of future work, so we want to add more examples. And in fact, a shout out to Hakan Kjellerstand. He has been a very active beta tester of CPMpy, and he's already written almost 300 additional examples of problems expressed in CPMpy. We also would like to see more of the advanced examples. That means paper re-implementations. So we welcome any paper re-implementations and to add them to the advanced examples. And we're going to continue to do this ourselves as well. We also hope to add more solvers, especially incremental solvers. So CPMpy itself is ready for incremental solvers, but currently only PySat truly supports incrementality of the solvers that are there, and so our tools doesn't yet. So we really welcome more additional solvers. And as I said, one of the ambitions, at least in our lab, is to use it to work towards conversational and human-aware technology for CP, and where you're always very welcome to join also in a structural way. Okay, so that was this tutorial. And this is again our webpage. This is the best possible kind of starting point to get started with it. And I'd be happy to talk to you at CP, or if you have questions, you can also mail me or post something on the GitHub page. Thank you very much.